This is the second video for Siemens Energy, Thursday, December the 7th. And what we're going to do on this video is, again, per connection diagram E1989. We're going to start taking our reading, our data. So we have the board enabled with 24 volts. And when the board has 24 volts and it's enabling and firing all four modules, the current demand is 210 milliamps per this for this DC to DC converter. The 24 volts AC requirement to power all four boards, the AC change, is 700 milliamps AC. This one 210 DC. Again, we notice that on the rectified 30 volts AC from the 24 for the board is 29.7. And can you move that, Tony, to the second or third board just to verify that that is right the case? The time. Oh, that's approximately the same, 29.7. Keeping in mind that there's 4 individual bridge rectifiers, so voltages will be there. Keep in mind that we are powering with 24 volts, not with 34 volts or 30 volts AC as recommended for that board. Seat high being 10 volts. We have minimum delay angle, so we are at 75 hertz and we are at 14 degrees. And what I'm going to do at this moment is I'm going to change the time. Going in the opposite direction, and I'm going to show just one pulse train. Right now the board has JU1 installed, correct, Tony? Yeah. Okay, so that's why we have a single 120 degree. Can you remove that JU1? Yeah, it's actually 230. Let's go ahead and do the 120. We're going to do it all with a single 120. And I'm going to open this up. This is, and the reason why I'm checking the 120 as opposed to the 230 is because these are the worst loading conditions. The firing board is giving you an output. So if we were to measure that, it is at approximately 3.5, 1, 2, and 3.5 division. So that's a peak of 700 milliamps for the initial, and if we go all the way to the end of that, it's at approximately 180, 150 milliamps. So let me go ahead and bring it back again. Tony, I'll appreciate if now you can move sig high from 10.4 to 0. And you notice that, of course, is changing. Are you there?
Yep.
Now what I'm going to do is I'm going to open this up just to show that now that it's at 0, this is a little less, but it's so this right here we have 1, 2, 3 and about a quarter. Hasn't changed much. And if I go here to the end of the trail, we're still on the 3/4 of a quadro, so that doesn't seem to change and shouldn't change as a function of sig high. So now I'm going to ask you, Tony, to change the frequency from 75 hertz to 60 hertz. Alright, that's good. Now sig high is 0, so let me just take a look at it there. So we notice that amplitude, it's still relatively the same. It's always between the 3.5 divisions or 700 milliamps. And if I go through the trail, again, it's about 3/4 of one division. approximately 150 milliamps. So while I'm there, can you go ahead and change the sync tie to 10 volts, Tony? Is the delay angle changing? I want to open it up again. So again, there's still that little shy of the 3.5, and if I were to move this over here, it's still 3/4, which does not change. Now I'm gonna probably repeat some of these readings. Let's go ahead and inhibit them. Now let's move or Pearson from the C output, the minus C output, from the first to the fourth word, and we'll repeat our reading. Okay, go ahead and enable it. Thank you. So we are at 60 hertz, and just go ahead and see if I can get my reading here. You have sync high 10, so there's my 14 degrees, and now I open this up. We notice that the amplitude of the initial pulse, it's probably again the same, 3 divisions and a little less than a half, and the end, or the trailing or last pulse on that pulse train, it's still those 3/4 of a division, or 150 milliamps. We could switch it around, but that should not change. Our amplitude should be the same. If you bring it to 0, just to prove that that's the case. Notice that it moved. There it is. But again, it's a little shy of the 3.5, and that is still within the 3/4 of that division. This is the end of the second video.